So let us end chapter 7 with a geometric example in section 7.6. Geometric example. And to look at such an example, we need to define what a convex subset is. So given a subset R of the plane, we say R is convex. R is convex whenever for every x comma y in R, the segment joining xy, which joins R, is contained in R. Okay, so for example, this is a convex region, right? Take any 2 points, it is going to be contained inside. So this is convex. Compared to that, this is not convex. Right? For a convex polygon, a diagonal is a line segment joining two non-adjacent vertices. A diagonal is a line segment joining two non-adjacent vertices. So first of all, what is a polygon? A polygon is a shape where every side is a straight edge. Okay, so for example, a pentagon or a hexagon or a septagon, dodecagon, all of these things are polygons. Okay, and a convex polygon, we know what a convex shape is, so it's a polygon which is convex. Okay, so n-sided polygon for a convex n-gon, the number of diagonals is equal to n into n minus 3 over 2, which one way to think about it is, each vertex, choose a vertex. How many other vertices can you connect it by an edge? Well, you cannot connect it to itself, and you cannot connect it by a diagonal to the two adjacent vertices. So that leaves n minus 3 options for it. Each of this, so there are n vertices, total number of lines you are going to draw is n into n minus 3, but each of the diagonals is being drawn twice this way. Once from the starting vertex to the ending vertex, and once the other way when you change your starting vertex, right? Another way to think of it is, well, how many lines can you draw for n points? Well, take any two different points, you can connect them by a line. There are n choose 2 lines you can draw. Which of these are not diagonals? Well, if you're connecting two adjacent vertices, right? In that case, it would just be a side. How many sides are there? N. So you have n choose 2 minus n sides. Okay, which is exactly n into n minus 3 over 2. So now we can look and define our problem that we are interested in. Okay, so for n greater than or equal to 2, let hn is equal to the number of ways of dividing a convex n plus 1 gon. Okay, so a convex polygon with n plus 1 sides into triangular regions by adding diagonals which do not intersect in the interior of your shape. That do not intersect in the interior. Okay, so for convenience, we take h of 0 is equal to 0 and h of 1 is equal to 1. So technically you don't have a regular polygon for 2, but we will take h of 1 is equal to 1 for convenience. That we will find later on. So how many ways are there? So let us look at some easy examples. Let us look at n is equal to 1, n is equal to 2, n is equal to 3, and maybe n is equal to 4. Okay. So n is equal to 1, we don't have a way, it's just a side, my convex polygon, but my h of 1 is equal to 1, right? For n is equal to 2, I have a triangle. I don't have a way of dividing it into triangles because it itself is a triangle, right? So h of 2 is also 1. H of 3 is a rectangle, right? And I have 2 ways of doing it, right? I have this and I have this. So h of 3 is equal to 2. N is equal to 4 is a pentagon. 1, 2, 3, 4, and 5. And as you can see from the number of shapes I have drawn, there are 5 ways of doing this. Okay, so there's 1, 2, 3, 4, and 5. So you can check that these are the only 5 ways. H of 4 is equal to 5. Okay, so I want to find what is the number for a general and find formula for Hn. Right, I want to find the formula for a general Hn. Okay, so what are we going and a recurrence and C-U-R-R-N-C-E and recurrence. So first we want to actually find a recurrence and then we can find a formula, because maybe while I said it in the reverse order, it is easier to find a recurrence than to find a formula. So let me show you what the method is going to be for some shape, how we are going to do it. So let me, for simplicity, draw an octagon. Okay, so octagon has 8 sides, and so I am looking at h of 7 is equal to question mark. I'm trying to find it. It's going to be a very big number, and we don't have an exact way, but here's how we are going to do it. We are going to designate one of the sides as the base. Method designate one of the sides as a base. Okay, and then I am going to divide the n-gon into 3 regions, one of which is a triangle with the designated base, one with k sides, and other with n minus k plus 1 sides. Okay, so how are we going to do this? For example, in this case, I am going to, let's say, this is my base. Okay, then what I can do is I can either divide it this way or this way, or that's a terrible color. Maybe this way. No, not that way. Oops. This way, right? And how many ways do I have of, no, I can do it this way. I can do it this way, right? That would still be a triangle with this. How many ways do I have of dividing it? So in the case of a 8-gon, here's what is going to happen, right? So let me draw 8-gon. 1, 2, 3, 4, 5, 6, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Oops. 6, 7, 8. And the final one. I'm drawing these because I know what it is going to be like. Okay. And in each of these cases, I have designated my bottom side to be my base. Okay. And then if with this designated base, how many ways do I have of dividing it into dividing it into triangular regions? So my first thing is I am dividing it into 2 regions. This is one big region and the other is just a 0 side region with 2 sides, 1 side. Okay, the other is this, right? So in the first case, I divided it into a region with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, and a 7 sides, and the other in what we will call as region with 2 sides. In this case, I have 1, 2, 3, 4, 5, and 6 sides, and 1, 2, 3. So 7 plus 2 was 9. Here I have 6 plus 3, 9. Let me go back. 1, 2, 3, 4, 5. And 1, 2, 3, 4. So 5, 4, 7, 3. You can see how this is working out, right? So this is going to be exactly symmetrically opposite, going this way. Three, four, five. Oops, I drew one too many. It should have been exactly 6. Right? And so what I'm going to do is I am going to divide it in this way, and then my problem reduces to, in the first case, this is now a 7 gone that I have to further divide. In this problem, I have a 6 gone that I have to further divide, and a triangle, a 2 gone, 3 gone. Here it's a 5 gone and a 4 gone. Here it's going to be a 4 gone and a 5 gone, right? Here it's going to be a 3 gone and a 6 gone, 2 gone and a 7 gone, right? So therefore, total number. So let me call these cases 1, 2, 3, 4, 5, 6. Total number of ways is equal to number of ways in number 1 is the number of ways of further dividing this 7 gone, which is, well, since it's 7 gone, it's h of 6, into number of ways of dividing the 2 gone, which is h of 1, plus number of ways of dividing my h of 5 into the number of ways of dividing the triangle, plus h of 4 into h of 3, right? 5 gone into a 4 gone, plus h of 3 into h of 4, plus h of 2 into h of 5, plus h of 1 into h of 6, right? So that is what I get as the total number of ways. So, well, the total number of ways should be h of 7, right? Is equal to h of 6 into h of 1 plus h of 5 into h of 2 plus h of 4 into h of 3 plus h of 3 into h of 4 plus h of 2 into h of 5, h of 1 into h of 6. Now, you might be slightly worried that, oh, I have only worked with one base, and what about the other sides? What happens? Like, why can't, what if I change the base? The idea is this is enough because once you divide it into sides, once you divide it into triangles, each base, each side is going to be part of some triangle in one of these exact 7 fashions. So this specifically chosen base has to be in one of these exact triangles. These are all the cases, as the designated base has to be in one of these triangles in the final division, right? And oops. And so this is not unique for an 8 gone. In general, therefore, in general, h of n is going to be summation k is equal to 1 to n h of k into h of n minus k plus 1, right? K greater than or equal to 1. And h of 1 is equal to 1. And let us check if it makes sense. H of 2 is equal to h of 1. Oops. H of k 8 7. Oops. Yeah, that's that should have been just h of n minus k. Oops. Okay, h of 2 is equal to h of 1 into h of 1, which is equal to 1 times 1, which is 1, and we know h of 2 is equal to 1. H of 3 is equal to h of 1 times h of 2 plus h of 2 times h of 1 is equal to 1 times 1 plus 1 times 1 is equal to 2. And both of these check out. So it checks out for lower levels, and therefore required recurrence relation is h of n is equal to summation k is equal to 1 to n. Oops, this should have been n minus 1. 1 to n minus 1 summation h of k h of n minus k. Okay, great. But there's a small problem. None of the techniques I did till now solve this double recurrence relation, right? None of the methods we used before had a product, right? And so we don't have a good way of solving it by what we did before. The only way we have of solving it is via generating functions. Use generating functions to solve this. Okay, so once again, generating functions is the only method that is going to work because none of the things we did before had anything of this sort being multiplied. So let g of x is equal to summation n is equal to 0 to infinity h of n x to the n. Then let us look at what happens when I take g of x squared. G of x squared is equal to summation n is equal to well, h of 0 is 0, so let me just go 1 to infinity h of n x n multiplied by summation n is equal to 1 to infinity h of n x n, which gives me summation I is equal to 1 to infinity summation j is equal to 1 to infinity hi hj x to the I plus j, which I can instead call x to the call I plus j as n, and then this is summation n is equal to 1 to infinity summation k is equal to, let n is equal to I plus j. So instead of calling it k, let me just stick to I. Then I is equal to n minus j. Since the minimum value of j is 1, I get, and minimum value of I is 1, I is equal to 1 to n minus 1 summation h of I h of n minus I x to the n. Okay, great, which is exactly equal to summation n is equal to 1 to infinity h of n x to the n, right? Because I know summation h of n minus I n minus I is exactly h of n, and so this is exactly my gx, right? And therefore, well, oh, oops, n is equal to, I forgot a small point, n is equal to 2 to infinity. 2 to infinity. Oops. So this is gx minus x, right? Because minimum value of I is 1, minimum value of j is 1, so I never get h of 1. The minimum I'm going to get is h of 1 times h of 1, which is going to be h of 2. So my sum starts from n is equal to 2. To take care of that, I have to put n is equal to 1. Therefore, g of x squared minus g of x plus x is equal to 0, right? We know how to solve for this. Therefore, g of x is equal to 1 plus or minus square root of 1 minus 4x all over 2, right? By the quadratic formula. So you take g of x as maybe y, and you solve for solve for y using the quadratic formula. And so now I have two choices. G of x is equal to 1 plus square root of 1 minus 4x over 2, or g of x is equal to 1 minus square root of 1 minus 4x over 2, right? And this one gives me g1 of x and g2 of x. This gives me g1 of 0 is equal to 1/2. And this gives me g2 of 0 is equal to 0. Well, I know that g1 of 0 should be just h of 0, right? Is equal to h of 0. Therefore, g of x is equal to g2 of x is equal to 1 minus, so this is not equal to h of 0, 1 minus square root of 1 minus 4x over 2, which is 1/2 minus 1/2 1 minus 4x to the 1/2. And the reason I'm writing it as 1 minus 4x to the 1/2 is because we can use Newton's binomial theorem to expand it, which is equal to 1/2 minus 1/2 summation n is equal to 0 to infinity 1/2 choose n, whoops, 1/2 choose n, 4 to the negative 4 to the n x to the n, right? And now what I'm going to write is slightly different. So look at 1/2 choose n. Well, this is equal to 1/2 times negative 1/2 times negative 3/2 times dot 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 negative 2n minus 3 over 2 all the way over n factorial. Right? This was my definition of well, what happens z choose n where z is not an integer, and this is equal to 2n minus 2 factorial over n minus 1 factorial times 2 to the n minus 1 multiplied by negative 1 to the n minus 1 over 2 to the n times n factorial. Okay, so if you want to know why this is, I suggest looking at page, this is at the end of section 5.5. So exactly page 184. This computation is given there. Page 148, not 184, 148, section 5.5. So look at that. It's an easy computation which is explained well in the book. So I'm not going to go through the complete details of this, right? So it is exactly this, and hence this is 1 over n, 2n minus 2, choose n minus 1, times negative 1 to the n minus 1 over 4 to the n times 1/2. Okay, so 2n minus 2 over n minus 1 factorial times n minus 1 factorial times n factorial. I pull out 1 over n, it becomes n minus 1 factorial squared, which is just 2n minus 2, choose n minus 1. 2 to the n minus 1 times 2 to the n is 4 to the 1, 4 to the n divided by 1/2, and I'm pulling out the negative 1 to the n minus 1 outside. Now this I can substitute back in my formula for gx. Therefore, g of x is equal to summation, well, 1/2 minus summation n is equal to 0 to infinity, 1 over n, 2n minus 2 over n, 2n minus 2, choose n minus 1, times negative 1 to the n minus 1 over 4 to the n times 1/2 multiplied by negative 4 to the n x to the n. Oh, I forgot a 1/2 here. 1/2. 1/2 summation, right? And so after everything cancels out, I am left with this is equal to 1/2 plus summation. The 1/2 cancels, 4 to the n, 4 to the n, negative 4 to the n cancels. I have left with the extra negative 1, which I cancel with the negative 1 on the outside, making it a plus. Summation 1 over n, 2n minus 2, choose n minus 1, x to the n, and therefore I get that h of n is equal to 1 over n, 2n minus 2, choose n minus 1 for every n greater than or equal to 1. Okay, and this is the end of chapter 7.